tell us about the Ligero.
Thanks, Omer. Hello, everyone. I'm going to talk about this work on lightweight sublinear arguments. This is joint work with Scott, Kermit, and Yuval. This is a couple of years old. I mean, with the pace at which we are developing zero knowledge, a lot has happened since this paper. Some of these slides are like 2 years old. I want to go over the construction that we have. And then towards the end, I'll try to talk about some of the extensions of the techniques that we have used in this work. So for the first half, it's about just giving our construction of a lightweight zero knowledge system. We're going to introduce techniques that have come from the MPC literature, or MPC, also popularly called MPC-in-the-head. This was one of my talks from the boot camp. I won't talk about MPC-in-the-head. You can go look at the video if you want to see MPC-in-the-head. But here, I'll just sort of try to give the construction directly. So, I was not here on Monday, but I'm going to assume Yuval had a great talk on taxonomy of zero knowledge systems. Zero knowledge indeed is a big party, as Yuval alludes to, and this is going to be. There are many ways of classifying proof systems. You want it only for deterministic computations, or NP, interactive versus non-interactive. Whether you rely on a trusted setup phase or are you transparent, you care only about soundness, or in addition, do you want zero knowledge, succinctness versus non-succinctness, and of course, there are many flavors of succinctness that are in literature. Then we want to talk about the cryptographic assumptions that are used in building these things. I sort of have highlighted green are things that that are more desirable than the red color ones. You want for NP, you want it to be non-interactive, not rely on trusted setup, require privacy, meaning zero knowledge, succinctness, and not rely on public key assumptions. These are sort of features that you desire in your proof system. There are many approaches here in this slide. Again, go to Yuval's talk to see all the taxonomy and how you can unify the different constructions that we know of. This slide primarily sort of shows where the combinatorial techniques have come from. And again, you can see everything ends at 17 because I haven't updated the bibliography since 17. But also, if I did do that, it's just going to overflow in this page. The three categories here are like things that have come from the classic probabilistically checkable proofs, the GKR style proofs. This is sort of the first category of constructing sublinear arguments. The second is linear PCPs. This is the one that's more popular in practice. It's in the Zcash zero knowledge system and many of the others like the bullet proofs, etc. And the third category is multi-party computation, and this is where Ligero sits. But I'm going to sort of say that, now that these things are getting unified, the things that come out of the multi-party computation indeed is sort of an interactive version of PCPs. All right, so what is the main result? Just theoretically stating is that we get sublinear zero-knowledge arguments without a trusted setup. A couple of features is that I'm going to describe this protocol on a high level. It is simple, it's concretely efficient, and relies only on symmetric key crypto. In fact, it relies just on collision-resistant hash functions for the usual reasons. So at the time this was published, we were sort of the first to achieve all these categories in zero-knowledge systems. It was sublinear for NP, did not require sort of complex PCP machinery, as I will demonstrate, and relied only on symmetric key crypto. And it was also something that we implemented. We showed actually this is concretely efficient in practice. Here are some high-level concrete parameters of our zero-knowledge system. Roughly speaking, we can show that if you want to construct a zero-knowledge proof for a circuit C, the NP relation expressed as a circuit C, then our proof length, the interactive version for 40-bit security is something like square root C, half of square root C kilobytes. Now, you have to apply Fiat-Shamir if you want to make it non-interactive, and then you have to instantiate ours with 80-bit security to get 40-bit security. And roughly, you can think of it as twice, but it's actually less than twice to get from 40-bit security to 80-bit security. And a proof system works both for circuits that can be described as, as a Boolean circuit with AND, XOR, NOT gates, or arithmetic circuits over some finite field with addition and multiplication gates. And when I say the size of C, it's basically the number of gates in your circuit. Specifically, actually, it's the number of you can think of it as the number of AND gates if it's Boolean, or number of multiplication gates in case of finite fields. Another feature of our proof system that actually yields us very good prover times. Like the prover time of our proof system is pretty good. Actually, even till recent works, it seems to be quite competitive in the past 2 years. And roughly speaking, the thing is that the number of fast Fourier transforms, which are employed in most zero-knowledge systems, we need to apply many, many fast Fourier transforms of a smaller size rather than one fast Fourier transform of the size of the circuit, which is typical in other implementation. And this has space as well as time implications when you concretely implement the zero-knowledge system. So what I'm going to do next is sort of give you a proof schematic of how our proof system works. Okay, so this is a circuit. Imagine this is the NP relation, which takes as input the witness W and outputs yes or no. So what do we do in the proof system? The prover feeds in the wires, the different colors depicting different values, evaluates the circuit, and then takes these wire values and it's going to arrange it in a matrix. Now, there is some method to the madness in moving from the wire values there to over here, but imagine that all these wire values are going to occupy some place in this matrix, and each of them is going to occur a constant number of times. It depends on whether it's a Boolean circuit or arithmetic circuit. The number of times we have to repeat matters, but it's either 2 or 3. And there is some flexibility in our zero-knowledge system in this part where you can decide on what should be, how fat or how thin your matrix should be, with the only constraint being that you would be able to put all the wire values in your matrix. In other words, A times B must be 3 times the number of wires in your circuit, because each wire value occurs 3 times. You can arrange, you can choose A and B to satisfy this constraint. And as you will see, the optimum way of doing this would end up with A and B roughly being square root C. And this is why our proof complexity is also, the proof length is square root C. So this is the constraint. A times B is X times number of gates. The Boolean setting requires X equals 2, where we count the number of gates to include both AND and XOR. But you can also think of it, you can also move to the arithmetic setting for GF2 and take 3 and count the number of multiplication gates. Both are, you can choose which one gives you better parameters. But the takeaway is that you have to repeat it 2 or 3 times in this matrix, and you need to arrange it in some specific order that I won't talk about, but this is the first step that the prover takes. Next, the prover is going to take this matrix and actually going to encode each row of this matrix using a code. And for people familiar with crypto, what we are doing is actually using secret sharing to secret share each of the rows of this matrix using what's called pack secret sharing. And I'll tell a little bit about this later. But for those not familiar with pack secret sharing, it's like a Reed-Solomon encoding of each row of this matrix. And another way of thinking of it is that this is also sort of an interleaved Reed-Solomon code, because you're just taking a direct sum of the codes in this matrix. Now, this encoding, we should ask about what is the expansion. It's going to be roughly, again, a constant. And if you ask what this constant is, it's something like 4. Okay, so from B, it becomes 4 times B. The number of rows, of course, does not change. So now here is our proof system, at least the schematic. So the prover first builds this matrix, arranges the wire values, encodes them. And then the prover is going to look at this encoded matrix, think of it column by column, put it in the leaves of a Merkle tree, and submit the root to the verifier. So it builds a Merkle tree where, in the leaves sit these columns. You build the Merkle tree, give that as the first message. The verifier now is going to do a bunch of challenge response. Yes?
Actually, sort of compiling an IOP into an argument?
Yes, and we'll get to that. You are actually, well, I mean, IOP is more general, IPCP, like you just need to send one. You don't need to send multiple. So you're compiling an IPCP, which I'll come to it in a bit. So the verifier is going to do a couple of challenge responses on what's being committed in the first round. So the verifier is going to give a bunch of, I'm going to give the finite field version, so it's going to give a bunch of random field elements, and the prover is going to give, is sort of going to compile the rows of this encoded matrix using these random field elements, and compile a row, and it's going to send that to the verifier. One of the things over here is actually you just take a random linear combination of the rows, and that will be one of the things that the prover sends to the verifier. This picture is not accurate. Actually, you send 2 or 3 rows of information. I'm just depicting one, but the amount of information you're sending in this is order B elements. Now, the prover has compiled these rows using some sort of combination and given it to the verifier. Now the verifier is going to check if these rows were indeed computed correctly from the rows that were committed in the first round. So the verifier is actually going to challenge the prover with a bunch of column indices. It's going to pick a random subset of columns from this encoded matrix, and the prover is actually going to give these values in the clear. Okay, along with the decommitments, to show that these columns were indeed the ones that were part of the Merkle tree. And we all know Merkle decommitments are efficient. You need to give sort of log n hashes to verify each column of this matrix. And the verifier is going to check that the information sent in the third round is consistent on these columns. Okay, and it will be the case that the computation that yielded these rows in the third round are column-wise operations. It's not like any mix of anything. So each column can be verified individually with respect to these rows. Okay? And the idea being here is that the verifier is just opening a subset of these things. Now, if the prover cheats in too many, it's going to be caught. So it will cheat only in a few. And now what we're going to do is that then it will sort of ensure on a high level that these codes that were submitted are good. Okay, they are good encodings and also will satisfy the right kind of relationships. And the relationships we care about here are, remember that what was encoded are these wire values. And you care if it's an addition gate, one is a sum of the, of its inputs, or if it's a multiplication gate, it's a product. Okay? So this is sort of the high-level proof schematic of our zero-knowledge system. The proof length is the rows, like 2 or 3 rows that you're going to send in the, this is sort of the dominating cost, like the third and the fifth message are the dominating cost. The third row is order B, and the last message is kappa times A. It's the number of columns that you open. How many do you have to open? Well, if you want 2 to the minus kappa soundness, then you have to open roughly order kappa columns. It's not entirely accurate, but you can assume for, just to look at what our complexity is, you can imagine this to be kappa. So this is sort of our proof length, and now you can see that if I want to optimize A and B so that my proof length is the shortest, it's going to be roughly order square root C. Okay? And the computation, if you look at what are the computations that you have to do? A, you have to encode row by row. And since you do this A by B, and each time you're going to encode B elements using Reed-Solomon codes, which can be done using FFT, this is like sort of, for each row, I'm going to do an FFT of domain size order square root C. And the overall computation is, for each row I have to do this, so sort of square root C FFTs of size square root C. Okay, so this is where the computation comes from. And the cost, actually, if you think about it, there is some amount of cost also involved in building the Merkle tree, but what's dominating is the FFTs. All right, so this is the proof schematic. Now I want to sort of give elements of what goes into this proof. What do we do, in these steps? Okay, and how are we going to verify that what the prover gave indeed are good encodings of right wire values? Okay, and the way I'm going to show it is using by demonstrating an IPCP. Okay, an interactive PCP, and you see how an interactive PCP is compiled. This is how you compile an interactive PCP. So I'll frame these tests that we are going to do. Imagine that I have the prover, it has this encoded matrix, and I'm going to give you tests on this encoded matrix that's going to give us the necessary guarantees on what the prover is encoding. Okay, I'm going to give 2 of these tests. But first, I just want to say one slide about this encoding. Most of you probably know already Reed-Solomon encoding. I want to give you the crypto equivalent, which is the pack secret sharing interpretation of this encoding. So everyone knows Shamir sharing, where you pick a polynomial, you put a secret in the evaluation point 0. Now, an extension of this secret sharing where I can store more secrets is called pack secret sharing. And roughly the idea is that you, instead of why stop at storing a secret just in P of 0, store more secrets in P of -1, P of -2. Now, what is the consequence of doing this? The threshold for privacy and reconstruction sort of gets affected. In standard Shamir sharing, this is 1 off, right? You have privacy up to T, and then if I have T plus 1 elements, I can reconstruct the polynomial. Here, to reconstruct the polynomial, I will choose a polynomial of degree T plus L, and the privacy still is up to T, but to reconstruct, I need T plus L plus 1. This is essentially what changes when you go to pack secret sharing from standard. And just going back to the previous slide, each row of this is encoded using pack secret sharing to get this matrix. Now, I said use P of 0, P of -1. In practice, you don't do that. You choose your evaluation points that are nice for FFT evaluations. And it requires something a little more than, it's a little more non-trivial than choosing evaluation points, because you actually need to do multiple things. You need to interpolate on this, and then you need to evaluate on 2 distinct set of points. So some amount of effort is required to make this work nicely.
How big can L be?
So how big should L be? Well, you can have L to be whatever you want. The question is, what happens to this, right? And L is going to be my B, and it's going to affect what I send over here, right? So L it's a parameter. You can fix whatever you want. So you first optimize your proof length and then get L. And again, I'm just saying it as though it is simple. You have to also, it affects the soundness computation, as I will show you. This T plus L and the number of how much you expand, you have to optimize the soundness equation if you want 2 to the minus kappa soundness. So you determine L first, and then you come here. So T and L you determine from your soundness equation, and then you can. All right, so the first thing I want to do is that the prover was supposed to take secrets and encode them. right? So this was the first step in the proof system. The first test I'm going to do is to check if the prover encoded it using the right encoding, meaning it took a bunch of secrets and encoded it with a t plus L degree polynomial. Okay? And remember, there are many, either you view it as an interleaved Reed-Solomon code, or you think of it as many, many rows of encoding, this fat matrix that you have. And we want to prove that each row is a good encoding, meaning there aren't too many errors, so to speak, in these things. Okay? And of course, there are many, this has been studied in literature. What we did is employ one of them, but give a new analysis for it. Okay? And the idea is simple. So I'm expressing this now. No longer I've moved from the zero knowledge to an IPCP model where the prover takes each column of this encoded matrix and is one symbol in my proof. Okay? And the goal for me is to test that the row-wise, each of them are valid encodings. Okay? So how does this go? So after the prover puts the proof in the sky, the verifier is going to do a challenge response. And the verifier is going to simply give random field elements, and the prover is going to give a random linear combination of these rows. Okay? So F1 times the first row, F2 times the second row, so forth. And that's what the prover is going to give. And the verifier, in the PCP model, you don't need to ask the prover to open. You can just go and look in the sky. You pick I columns, and you look in the sky what these values are. And then you're going to do two checks. You're going to check that the random linear combination that you got from the prover has the right degree. Well, if everything was degree at most t plus L, then the random linear combination also should have degree at most t plus L. And, okay, it should be t plus L, but you understand the point. And you check if the row that you gave agreed on those points. Okay? Now, this again is sort of an idea that has been there and time tested. But the point is, what are the guarantees of this test? And one of the things that we did in our paper is analyze it. And this is probably the most technical part of the talk. Let me just explain what we showed. Okay? Yes.
Degree at most t, you just interpolate and see.
I mean, the prover is giving the polynomial. If it gives more than t plus L plus 1 coefficients, you reject. Yeah. I'm saying you can give the polynomial instead of the encoding. I mean, again, like if it didn't, then you have to interpolate. So basically, in this test, what do we want to do is that so think of the matrix U star, which is the matrix that the prover, combining the columns of the symbols in the sky. Now, you want to ask how many columns of this have errors across the rows. Each row needs to be a valid encoding, and you're going to ask how many columns have these errors, and you want this to be small, or at least you want the verifier to reject if a lot of these columns have errors. And what we are able to show is that if E is less than the distance of this code by 4, then, and if the matrix had more than E columns of errors, then the prover will get away with its proof with probability at most this. Okay? And the 1 minus E over n to the t comes from, I'm choosing to check if things are fine. And the second part of it is sort of the non-trivial part of how we show that it's E plus 1 over F. Okay? So this, I'm just trying to explain the part is like this sort of influences what proof lengths we got. And we were able to show this only for E that was less than distance by 4. And this affects how much your expansion, how much do you have to expand your encoding. Because E has to be at most D by 4, and to make this soundness less than 2 to the minus whatever you want, it affects those parameters. And if we could improve this E to much closer to D by 2, it would improve the parameters of our proof system. And
why not go to multivariate to
read Muller codes? We didn't analyze, this analysis worked only for...
Is there a reason why not? Maybe you can make it shorter, right?
So,
shorter?
Wait, why it won't make it shorter? Meaning, I mean, you have to worry about packing. I mean, this is not the only thing that we do. So, I mean, in Reed-Muller, I'm assuming you'll have to pack it in a different way. So it'll affect other things as well.
I mean, your rate will go down.
Yeah.
Either you blow up the block length to get constant distance, or if you keep your block length to be like proportional to the message length, your distance will be bad.
I see. Okay.
But you know, soon after we actually, well, Yuval contacted a couple of mathematicians, and they were able to improve this to E less than D by 3. They did it independently, and the second term sort of got a little bad, but it was still, it's still good enough for large field lengths, and we could improve our concrete proof lengths for this thing. And you can also ask, okay, what about E less than D by 2? I mean, this is a good mathematical question. If you want to try solving it, it's good. But for us, I want to say that it doesn't quite help us improve the proof length beyond a point, because there's also the Merkle tree and so forth. Like there are other factors that affect our proof length, and going to E less than D by 2 might not necessarily give us too much benefit. All right, so this was the first test. All we did was that whatever the prover gave, we checked that it had good encodings. Or rather, the number of errors in each row of this code was isolated to at most E columns. Okay, so now I'm going to give you another test, and here I'm only going to give you the test on how we check multiplication gates. Okay, addition gates requires another test. I'm not going to talk about it. You can come and ask me after. But let me just tell you how we are going to show that multiplication gates were done correctly. So imagine that the prover take the circuit, think of it layer by layer, and each layer has some number of parallel multiplication gates. Okay? Now, let's say that the blue and the red are sort of the left and right wires in each layer, and the green is the output of this layer. Now, what you want to check is that the first blue dot and the first red dot gives the first green. Okay, so you want to check this element-wise if this product holds. Okay, and I'm going to give you an IPCP test for checking this. And the reason I arrange this as a matrix is because I want to do pack secret sharing row by row. I want to amortize the checking of these multiplication gate row at a time. So you take these rows, blue, red, and green, and you're going to encode them using pack secret sharing. Okay, this is just as before, and I'm going to assume that I already did the checking the interleaved Reed-Solomon code part. And now what I want to check is that the secrets that were encoded in each of these satisfy this multiplication relation. Okay? The idea is going to be that, again, the verifier is going to give a bunch of random field elements, and the prover is going to take, remember that there is a polynomial interpretation for each of the rows of this matrix. It's going to compute the polynomial for the blue times the red minus green. Okay? And the idea here is that, remember, the secrets were stored in P of 0, P of minus 1, so forth. Now, when I do this multiplication, it would component-wise multiply the blue and the red values. And then when I subtract it with the green, if the prover was honest, the secret should have gone to 0. Okay? And then I'm doing this row by row, and I can combine them using a random linear combination. So I check all of these row by row and element by element in this one row. Okay? And once again, the verifier has to check whether this was computed correctly. It's going to open a bunch of columns, and it's going to check if the polynomial is of the right degree and if it agreed on all these columns. The only difference is that now the degree is twice. Okay? And we can show that this has good soundness, meaning that if everything was a good code word with the errors isolated in E columns, and if the prover cheats in these values, it will be caught with very high probability. So this way we can check all the multiplication gates in our circuit. And I sort of want to point out that we don't care about the circuit being wide. because the witness has all the wire values. So you can just take the first, to make it into blocks of L, you take the first L multiplication gates, the second L multiplication gates, and you can do it. This doesn't impose any constraint on the circuit being wide to do this. Okay? And another thing that you will see here is that for this test to work, I need the left wire, right wire, and the output wires to be aligned. And only then will this test work. Now, which means that, if I put all the output wires and then look at the next layer, I have to rearrange them so that they are left, right, and out. So this is why I will have to repeat a wire more than once. As I said, 2 or 3 times, I had to repeat it. I'll have to repeat it more than once. And I also need a test to check whether, 2 rows are it's a permutation of one another. And what we do is that we just generalize that to saying, look, I can check all linear relationships between rows. So you can imagine your circuit as a bunch of multiplications, additions, and this permutation and additions both can be thought of as a linear operation from one row to another. And there is another test that does, just like I say an IPCP for quadratic tests, we have an IPCP for linear equations. Okay, and I'm not going to talk about that, but if you want, come and ask me. It has a similar flavor to this, and it will involve the prover giving another row. Okay, and this is it. So our whole proof system is about first encoding the wire values in a matrix, do the so-called degree test, checking that each of them are a valid encoding, check multiplication gates, check addition gates, and the wire connections. And this is our entire proof system, and you have to optimize the parameters to get to find the shortest proof that you would need. So I explained all of this in the form of an IPCP, but morally speaking, all these techniques came from the MPC literature. And the viewpoint from sort of MPC in the head is that we use MPC in the head. We can take, there is a corresponding honest majority multi-party computation equivalent to our proof system that can be shown that we compile from that to our zero knowledge proof system using the ICOS transformation. Also, we had to optimize this. And I want to say that we are not the first to take something, an MPC in the head approach. Actually, it was first done by Giacomelli et al., who considered a much more simpler MPC protocol to get it. And I sort of want to point out that for some parameter regimes, using a simpler MPC can give you much faster provers. Maybe you will have to compromise on your proof length, but it can give you much fast provers.
I mentioned in my talk, and I don't know to what extent it's useful, is that the R works on MPC for linear algebra over non-abelian groups, and all these things can be translated here, and at least in the context of other proof systems, people haven't explored these types of generalization.
Yeah, and I mean, this way of viewing it, actually, I'm going to give you some more applications of this MPC in the head in the secure computation literature, and also tell you some of the things that we have borrowed from here. This is an approach that has much more versatility than the way we have used, and this is one of the things Yuval is saying. And there is some work that we are doing where actually it's even fine. So the verifier opens T columns. Now, it would be even fine if the verifier got some leakage on the remaining columns. We can use some leakage resilient properties of Reed-Solomon codes to say that even if it got leakage on the remaining columns, we would still get the zero knowledge of our protocol. And we haven't been able to use this to construct zero knowledge. I don't know, maybe there are these recent works on accumulators, which I don't know if it might help if there is also leakage on the remaining columns. Again, I've not made any thought into this, but this is a good question to think about. If I can also have leakage on the remaining columns, can I leverage this to get better proof systems? One thing I want to point out here is that typically when you think of MPC in the head, you think of classic like BGW protocol or so forth. And the first question you ask is how do you get sublinearity? You should think of each column in this matrix as a view of a party in an MPC in the head protocol. And the view of a party in typical MPC protocols is actually linear in the circuit size. Okay? And we are opening T columns. Each of these columns must be linear in the circuit size. How do we get sublinearity? And I mean, we saw it from a schematic point of view. We use pack secret sharing. That's how we got it. But from an MPC viewpoint, actually, the thing is that you have good MPC protocols where the total communication cost is amortized. There are works which show that you can have an MPC protocol where the total communication across all parties is circuit size, which means per party it becomes it's divided by the number of parties. And we opened only like sort of T columns from T views of this MPC protocol. Our contributions, just to summarize in this aspect of it, was that we optimized this ICOS transformation to work for certain kinds of MPC protocols, and then we optimized the underlying honest majority MPC protocol, which was sort of based on this work of, Damga Desai 06. And what I presented before was sort of from MPC, from MPC-in-the-head or from MPC, you get actually an interactive PCP, and from interactive PCP, you use standard compilers to get zero knowledge. So this is another way of looking at what we did in this work. Okay? So this sort of ends the Ligero part of my talk. Now I want to sort of tell you a little bit of follow-up works that leverage this MPC-in-the-head and probably shamelessly plug in some of my recent work as well. So the first work that I want to talk about is this beautiful work of Isha et al. That show how to construct actively secure multi-party computation protocols by combining elements that are sort of weaker, but also in a modular way to sort of get the benefits that Yuval was talking about. Like if I can break it into components for which I know some efficient protocols for one or the other, then a general transformation sort of helps me to leverage these benefits. So on a high level, again, I'm not going to define secure computation. Elon didn't define RAM programs, so I'm also going to take the liberty and not define secure computation. I sort of going to give you a high level here that what we want is, so this paper was about getting active security, meaning adversaries that can arbitrarily deviate in secure computation, and against a dishonest majority. Okay? And the high-level thing that this paper showed was that you can take two protocols of different sort of features and combine it to get it. So actually, these two sub-protocols that we talk about are going to have weaker security guarantees than what we want. The first one is an active multi-party computation, but against an honest majority. And the second is a passive two-party computation with a dishonest majority. And you can combine these two elements to get it. And these are the two pictures sort of that I have shown over here. This is active multi-party computation with an honest majority, where you can assume that the adversary corrupts at most one of the clients and at most half of the so-called servers in this computation. And this is dishonest majority passive secure computation. For if you want to think about it, just think of this as GMW, right? I mean, if I want to securely compute something, I just do gate by gate. I have additive secret sharing, and then to multiply, I employ either oblivious transfer or oblivious linear evaluation gate by gate. Okay, so these are sort of the two elements, and the idea is that both of these we know how to do very efficiently. And combining this, we could leverage the efficiency of both of these to get an active multi-party computation with an honest majority, with a dishonest majority. And I want to say that we have a work that sort of shows that this is actually concretely efficient. And the idea was that we used the MPC-in-the-head that we deployed for the zero knowledge proof system. We used it over here. Again, it requires quite a bit of work. I'm just simplifying saying that we use this, but the ideas that were employed over there, we could port the efficiency over here. And sort of the high-level taking point of this was that we could get active security where the total price we pay is roughly twice a passive, the one in the second category. And this is sort of, I'm going to talk about in the next few slides a little bit, but this is something that we care about. Like, we know how to do passive protocols very nicely. And most of the current approaches, at least the concretely efficient one, says repeat it like many, many times, do some cut and choose, and get active security. And the blow up seems to be proportional, sort of linear in the security parameter. And this sort of, is showing that, well, if you do this sort of combining these two ingredients, you can get an overhead that is kind of independent of the security parameter. We can get it to be like constant. And this work is going to appear in CCS this year. We actually implemented this, and this approach actually beats most of the concrete approaches. This works. I mean, what we have done here is only for arithmetic computation, so it works for large fields. What I'll do in the next 5 minutes is sort of just give you a flavor of how, and just connecting this to what we saw before. And what I'm going to do is that I'm going to take a very simple functionality and show how to go from passive to active. Okay? And the simple functionality I'm going to take is how you do secure multiplication. Okay? If I have field elements, if I want to do secure multiplication, I actually use this box that's called Oblivious linear evaluation. And this is a generalization of Oblivious transfer. You have a receiver that has an input x, and the sender has two field elements a, b, and the goal is for the receiver to learn ax plus b. Okay? And a simple instantiation of such a protocol, you can use an additively homomorphic encryption, encrypt x, and the operations that the sender has to do is like scalar operations on the ciphertext. You can get it and get the answer. But this only gives you a passive implementation. Now the question is, how do I get an active implementation of an OLE?
So do you require the same hiding compared to OT? So X is hidden from the sender and A and B are hidden from the receiver?
Sorry, can you repeat that?
You require the kind of same secrecy properties of OT? So
Yes. Yes.
From the receiver.
Yes, exactly. You need the same security properties. Viewing this over GF2, you can show how to implement OT using this box. So how do we do passive to active? I'm going to give you an honest majority protocol-ish for this thing, and then we can throw it into the IPS compiler to get an actively secure version of Oblivious linear evaluation. Our benefit or our strength will come from when we want to implement many, many parallel OLEs at the same time. And in fact, in most applications, it's enough to think of parallel OLEs because you can pre-compute what I would call like random triples or random doubles ahead of time, and then you can use it in the computation. So you do want this sort of a functionality where you can evaluate many, many parallel OLEs at the same time. So you can imagine the sender, each of them having m parallel OLE implementations. I'm giving you sort of the MPC version of this. The compilation works using IPS. So you should imagine that Alice takes her inputs, encodes it using Reed-Solomon codes, or pack secret sharing, and sends it to the server, and so does Bob. And now you can think of it, each server has to locally do this AX plus B computation on the symbols of the code. Okay? And the servers do that and then give the answer back to Bob. Okay? So this is the MPC sort of version of doing this. Now, to make this actively secure, you need two things. You need to make sure that everyone encoded things correctly, and you need to make sure that most of them did the computation correctly. Okay? This is similar to what we saw in the Ligero, where we wanted to see most of the columns were fine, and the errors were concentrated in a few, and these relationships were good. Right? So you can do similar things over here. I just point out that in the MPC version, you can think of it as after they compute, the servers do a coin tossing to get random elements, and then they broadcast a random linear combination of their values to check that they are of the right degree. This is sort of the interleaved Reed-Solomon testing that's featuring in this MPC protocol. And this is it. And after this, the servers give the answer to Bob, and Bob from C1 through Cn can reconstruct the product. Then you optimize these parameters, and you can show that each of these will be implemented when you compile it in the IPS framework. You will compile it with a passive implementation of OLE. Okay? And both the sender and the receiver will actually check if these computations were done correctly in a subset of these servers. And this will guarantee that most of them were done correctly, and that it will be part of checking this encoding. I know I'm jumping ahead a lot, but the point is all the elements that we used in the Ligero construction for doing this can be incorporated in this framework. Yes?
Factor 2 come in?
So, I mean, first of all, I need to multiply, right? So, I mean, when I do this encoding, my degree has to be at least twice. So that's why the n must be at least twice m. So this gives a good passive to active OLE, and this we actually benchmarked in our paper. So I want to say this has many features. I'm not going to get into this. Actually, one thing I just want to point out is that we can even weaken beyond passive OLE. We can even consider OLEs that are leaky. Okay, and because of this leakage resilience property of Reed-Solomon codes that I told you about. And by weakening it weaker than using a passive OLE, actually we have identified some parameters where our actively secure protocol is better than the best current passive. I mean, it's just an exaggeration a little bit, but the point is that we can get something, we can get active security directly from these leaky versions or imperfect implementations of OLE. And this is also one of the things that Yuval was saying, like this framework helps you to weaken things and identify better implementations of this. And I sort of want to say that this is concretely important because if we use additively homomorphic encryption based on LWE kind of assumptions, by making the parameters aggressive, they could become leaky, but still we could use it in our protocol. So this is sort of, I want to just frame this in a little more general way. I want to sort of say that we want to, as a general goal, to get active security that matches the cost of passive security. Now, if I frame this as the most general theoretical question, people are going to say, oh, I'll use generically used techniques like zero knowledge, sublinear zero knowledge, and so forth. So just to make it a little more the question that have practical or concrete implementations, you want to like sort of think of it as in a hybrid. Like you can frame this question saying that, look, all I can give you is OLEs. Now show me how to compile passive to active and tell me what is the overhead. And I sort of want to say that this in general is, if you ask for the most general question, Boolean, arithmetic, small number of parties, large number of parties, honest majority, dishonest majority, the most general sort of question, order S still seems to be the state of the art. Okay? I mean, we showed it for the two-party case, and there are other cases. Actually, if you consider large fields or small number of parties, we can make the overhead constant. Like previous work has shown how to make this.
Statistical security parameter?
Yeah, S is the statistical, good point. It's the think of it as 40, 128 or whatever. Okay, it's the statistical security. As I told you, often getting active security is repeating this S times. So this is the overhead. And I mean, actually, this is constant in theory. If you look in practice, it is 15 to 30x overhead. So there are also even the constant ones you care about reducing it. Okay, and we showed it only for the two-party case, and large fields we made the constant too. And here I want to say I have some recent work that sort of shows using this kind of not IPS framework but a generalization. The IPS framework works only for constant number of parties. If you want scalability. So we have an extension where we can make this constant for all categories, and I just want to be particular here that I'm talking only about communication overhead and not computation. Okay? And you can also ask that question, can I also get computation? And this is an open problem. Like, and there is again some work for large finite fields where they show how to get constant overhead, but the question still for getting constant computational overhead is still open. So this is this line of work. Now I sort of want to say that, okay, all this modularity is great. I mean, the motivation for all of these, the ICOS MPC-in-the-head transformation or the IPS was to get a modular approach of getting active security. Okay, and it was initially studied from a theoretical perspective, but some of my recent works have shown that, well, if you optimize these things, you're going to get something concretely efficient. And it sort of justifies why we want to study black box sort of constructions in weaker primitives. Okay? So that's regarding first application. Now I want you to forget this, and I want to tell you that we can actually use the state-of-the-art zero knowledge to also improve non-black box constructions. So I'm going to say that, well, our motivation to do these zero knowledge came from black box, and we got all these efficient things, but now actually we can show that we can take this zero knowledge and also prove something efficiently of non-black box stuff. And here I'm going to talk about secure two-party computation. In the interest of time, I'm going to skip the certified oblivious transfer, but I sort of going to say that here is a secure two-party computation. I mean, this is, in the past decade, people have been studying using garbled circuit, getting passive to active, and now we have a recent work where all we are doing is send one garbled circuit and prove that this was correct. And this involves non-black box. It requires us to prove things about cryptographic operations. In particular, you want to prove that an AES was done correctly. And actually, we can show that this is in the concretely efficient regime. It has some nice features of it being non-interactive. I mean, the current state of the art requires a few rounds of interaction. But we have a version where we can make this non-interactive by using this zero knowledge system. You can ask me later about this work. So studying black box also helps in sort of non-black box stuff.
So this outperforms the black box NISC protocols?
So if I have to, so I'll tell you later. So it does outperform. I mean, it's hard to compare because you can think of this as offline and online where, or as Yuval says, he talks about the silent pre-processing. So here you can think of there is sort of some offline phase where both of them announce something. The garbler puts garbled circuit plus proof. The evaluator just puts the OT first message. Then in the online phase, I send one message to you, which is the OT response. Now, if you look at the online phase, it's like as efficient as any passive. The offline proof part will take, again, the current zero knowledge systems make this very efficient, but that's the most computationally intensive part. And it also has nice features that, you know, the garbler can post the garbled circuit plus proof, and you can, like, publicly verifiable. The evaluator doesn't have to verify it. It can be attested, you know, by third parties ahead of time. So these are some nice features by just using garbled circuit plus zero knowledge. So just coming back, using this MPC in the head, we got some nice features. We implemented it again, like trying to tighten these nice black box modular transformations from MPC literature to zero knowledge proofs. There is ongoing work. We want to improve the complexity. Can we shorten the proof by using some recursive ideas here, but still keeping the prover efficiency? It seems, at least even till today, the Ligero zero knowledge system has a competitive prover. And you know, we want to think of improving this proof length without compromising the prover time benefits that Ligero has. And also, as I mentioned, about getting active security for multi-party computation using these techniques. And actually, there are many questions here. I mean, I've been talking about the zero knowledge based on MPC, but what about other zero knowledge systems? Do other IOPs help you do active security? And this is also questions that we can think about. And at last, I'll just leave you with one quote, which Yuval says is that honest majority is useful even when there is no honest majority. Thanks. Yes.
I'm curious if you have an understanding, and that was the right pronunciation?
Sorry, Ligero, it's Spanish.
Do you have a good understanding of what is the, say, largest bottleneck there? Is it the square root t coming up? Is it?
So when you ask bottleneck, I mean, are you talking about just proof length?
No, I'm asking what is concretely when using this thing.
Yeah.
What would you improve to make it more efficient?
So the proof length, and I can sort of let me just see if I can just quickly. Let me just tell you one thing. Like, I mean, how would one improve the proof length, right? I mean, the two competing factors are this and this. Okay. Now, what we can do is that this one we don't really need to send the whole thing, right? I mean, what do you care about? The degree of this, and you require like 2 tests on this thing. Now, you can imagine an IOP applied to doing this, which means I can reduce this. Okay? And now I can make possibly my columns fatter. Okay? So there is a trade-off here in that now you can ask, why don't I just do everything? Like, just one row, right? Put all the wire values in one thing and do it. Sorry? Exactly. That's my point. So there is sort of a regime to go from Ligero to Stark or Aurora, but there might be a nice sweet spot where you have good prover efficiency and also reduce the proof length. Yeah.
Well, maybe to add to this, the main advantage of putting things in a root n by root n is that you remove one of the major bottlenecks, which is space. So here you could process each FFT one at a time, and you'll be able to go much farther than you would with at least monolithically handling the large FFT. So this is something that you gain in, let's call it, scalability to largest instances.
Yeah.
In both cases, something that gives concrete improvements is a tighter understanding of this random linear combination. In pretty much every efficient IOP and IPCP, there is this random linear combination of Ritz-Solomon code words into one, and we don't have a tight understanding for that yet. There's some progress on that front from the deep fry work, but you can even change the linear combination itself.
So the deep fry sounded pretty tight. So what is the?
You can actually change what you actually physically do. It's not a linear combination. You can combine it without the domain sampling, and you will get slightly better. But more generally, there is this overarching problem of how do you combine many code words into one. Progress on that will improve things like this, and pretty much.
Some form of the.
Yeah. Right.
What you want is a multi-low degree test,
Right.
and the way we implement it today is a randomized reduction to single retest.
And if I have 1 minute, I'll just say one more thing about MPC in the head over here. This gives an interactive PCP. If we used like a different form of an MPC, we could actually get a PCP where the symbols are roughly square root size. And this might also, the MPC, again, it's the concrete efficiency, this is something that we are trying to find out. But in the designated verifier case, this can be probably useful in sort of a streaming model. I give you a K out of an OT, where I send you the first message. Now you send me the second message, where each of your n elements are these symbols. Now, if I can process my circuit in layer by layer and generate this, I never have to store the entire circuit in my memory. So not being an interactive PCP helps, because if it's interactive, I have to remember the entire matrix to do all these random linear combinations. But if you use better MPC protocols, one can also get sort of the streaming where you can generate the proofs on the fly and give it to me via an OT channel. So, this is something that, again, we are exploring. I can tell you a little bit about this as well. Thanks.
Any more questions for Muthu?
I have a question. So you mentioned that there's a literature on sublinear MPC, and one can even go, lower the complexity of it. You can even go lower than what you get here.
Square root. Yeah.
Is that possible?
Yeah. As I was telling that this one,
Yeah, but there's always a trade-off, right?
Yes, and
It's not like you remove it from one place and you put it in another place. What I'm asking is it just do we know a lower bound that there is?
it's actually an open question. So let me tell you that you're asking about the concrete prover complexity over here. Our complexity is like this n log n, because you're doing these FFTs. Now you can ask, can the prover be like linear in the circuit size? And there are recent proof systems that does it. There's a paper by Groth et al. That shows, but that's not yet concretely efficient. You can show asymptotically that for large fields, the prover has a constant overhead. The question for Boolean is still is open. We don't know how to get prover complexity that applies only constant number of Boolean operations per gate of the circuit. I don't know if that answers. Prover complexity is what you're trying to do, right? If you don't care about prover complexity, you can use IOP Stark Aurora and make it as short as possible. But if you're asking about prover efficiency, this is still an open question.
I have one question.
Yes.
So you mentioned the application of using these argument systems to prove the correct garbling of a circuit. Are you applying, in that case, general purpose argument systems, or instead maybe something more specialized that works particularly well when you have repeated subcomponents? Because in that case, you would be proving repeated application.
There are multiple aspects to answer your question. One is yes, like you're doing many AES evaluations, and that helps in our system because doing many parallel evaluations helps because I can isolate each instance in a column of this matrix and things that are benefits, sure. But the second thing is that I said we're doing non-black box. We're proving that AES evaluations were correct, right? But now I also need to prove that my OT messages were correct, which is like public key operations. And the way we found a sweet spot is we are non-black box in AES, but black box in the OT, because that helps us. So I want to say, yes, there is something tailor-made for doing it, and it helps to think of it as MPC in the head. But I'm sure that there are good questions to think about how to get it. What is the more clean question to ask over here?
Well, let's thank Muthu again.